In this, I'm going to cover the debugging side of things, mostly for debugging compiled C and C++ applications. So debugging applications varies on an operating system by operating system basis. There's a lot of tools on Windows for debugging. The two that I've put down are Visual Studio and WinDebug, both made by Microsoft. WinDebug has a couple features that Visual Studio doesn't. Visual Studio is a package I feel more people will be familiar with. Windows also has third-party tools such as OllyDebug. I believe the Immunity Debugger works on Windows too, but I'm not going to cover these. On Linux, we'll be using GDB, which is the GNU debugger. It's a little harder to use than Visual Studio or WinDebug because it doesn't have a UI, but it's about as powerful when it comes to the actual debugging. So Microsoft's Visual Studio is possibly the most streamlined of the debuggers. It's built very much with the idea of being an all-in-one tool for developers. The biggest things I think that I've commented on are the disassembler, the memory viewer, register tracking. I'm also including watching local variables in register tracking. So to quickly explain what's going on in this program, it's nothing overly complex. It's basically a wrapper around pointers in C. This is written in C++, but it's built around C and provides a safe way of deallocating and allocating pointers that forces the memory to 0. A kind of pseudo security thing. It's pretty basic. There's a lot of template type names. Don't need to worry about that. But the most important part is that I have a breakpoint set on this loop. That is where we print it. And this is only done here because I want it to already have set some values in memory. And it's initialized to 0 using this function, which is realistically just calc, but done by hand. And we'll set the first 128 values, or well, the memory allocation is only 128 bytes. We'll set 128 bytes to their respective values and then print them. But we'll break on the print and we'll have a look at the memory. So if we go up to local Windows debugger, then we can apparently lose the window. Behind Visual Studio there is a black terminal window that we don't really need to see. It's showing nothing right now. But we've got a breakpoint. There's nothing too important in this view. This is the source view with some annotations. The only arg we have past this function is the name of the exe. That's a C thing. And for the most part, there's nothing interesting going on. This is a very simple program. So there's nothing really interesting going on in the source disassembly, in the source, but the disassembly has some interesting things. So this is one of the more powerful parts of the debugger when it comes to working out what happened and why your code is doing certain things. So this loop here basically compiles to a jump and a bunch of instructions, and then a condition will check. There should be a compare somewhere, which looks like it's up here. This will compare this value, which is a D-word pointer. And if I had to guess, sometimes hovering works. Yeah, it does. This is a dereference, by the way. Brackets in Intel assembly are dereferences. So this is just checking against 128. Yeah. So this is just the check here. This is checking that I is less than 128. Specifically what it's checking is that when I equals 128, it's going to take this jump. And this jump goes somewhere. We could track where it goes to. Looks like it goes to here. I could be wrong. No, it goes to here. So it breaks out the loop here. Yeah, basically for 128 iterations we do not satisfy this jump equal statement. So this compare does a comparison and stores it in a register, and we then use that to check those. This will not be true until I is 128, so at that point we will jump. But until that we will just continuously loop, and this bottom jump here is an unconditional jump that just goes back up to the start of our loop up to here, which will move the EAX register, which is usually done as an accumulation register in Intel. In this case, syntax can be a bit weird to read. We move whatever value I is into our EAX register, we add 1 to it, and then we move it back. So we're just incrementing by 1. That's what these 3 lines here do. Nothing too complex, but the interesting one is this thing here. Call this out because it's an interesting line. This is the load effective address command. What it does is it loads the effective address at this pointer location, which tells us to dereference this variable PTR and store that address in ECX. This is what we'll use to actually do this dereference here. And then there's because this operator is overloaded to enable something, we actually have a call here. Otherwise we just index into it if it was a normal C array. But it's overloaded, so we have a function call instead. And then we have a print. At least that's not actually quite a print, but it's setting up the print statement. A lot of this stuff is just the standard out. And we have a standard inline. But as you can notice with where we've broken, we have the current register values for EAX. So this is in hexadecimal, 80 is 128. So we've reached the end of our loop and we've broken out of our statement and ended up down here. And EAX, by the looks of it, hasn't been touched since we did this other loop. Because if it had been, this should be lower, because we should have broken earlier. We can press F10 up here to step over, and yeah, that that immediately clears EAX, but EBP is still set to some pointer value by the looks of it. I guess that's what we're storing our pointer in. No, we're not. Not sure what that value is. It's doing something. Yeah. But other things we can do, we have local variables that are tracked. You won't get this view if you're debugging an exe that doesn't have its debug database. Although anything in the challenge should have its debug database on it. The use here is that we can actually look up this memory address. And I already have this memory thing open here. If it's not open by default, go to debug, and in Windows there will be a memory, and there's 4 views for memory. There's also disassembly here and registers here if it's missing. Mine was missing initially for some reason. So that's where it is if it disappears. And we can look up this memory location. And this is the start of our pointer. This is the memory allocation that we did earlier. And you'll see that starting from here, all of this memory is going up in increments of 1 until we get to 7F, which happens here. And everything after that is kind of junk. This is actually meaningless. It's just whatever was previously in RAM is there. If you scroll down a little bit, sometimes there is some interesting data. It doesn't look like there's any this time. Last time I did this, there was some stuff about my drivers sitting here, which was interesting. some stuff about hard drive volumes. Yeah. This is the actual Windows device location. There's a whole bunch of weird things in memory that you'll find. Anything with question marks, I think, is non-allocated memory. There's some... Yeah, here we are. It's above it this time. We've got things like our path variable with stuff in it. Yeah. Those weird things in memory. One of the things we can do, if we have source disassemblies, is we can hover over values to check their internal values. This doesn't work so well here, because although this is a char array, the first element of a char array in this case, because we started our loop at 0, is 0, and 0 is the null terminator byte, so we don't get a string because there's no string to print because it ends at the beginning. But if this was actually like a string of something, then it wouldn't have a null terminator at the beginning. So I mean, we can check something. We can try and write to it if we were really feeling brave. We could see if it's possible to rewrite, and apparently it is. So I just overwrote one of the values in memory there. So now we seem to have, if we hover over a pointer, it's not going to do that. But it is showing us here at the very least. On standard arrays, if you hover over them, okay, sometimes when you hover over them you get it. We now have a printout that isn't just blank because we don't have any null terminator until the end of the array. So we're actually getting way too much printed because we keep going until we hit 0, 0. I think that's really all that needs to be covered in debugging. Other than F11 is step into, so we can step into the function. The steps into our address of operator, our dereference operator. And it's not too much to, like, this is just weird. It's not very well templated code. So one other further thing I forgot to mention is the Visual Studio and WinDebug. Well, WinDebug's a little bit more clear about this. Can open exes that aren't within a compiled project. The way you do that is you go open project and solution. And if you notice in here somewhere there is exe project files.exes, and we can just browse to the location of an exe and just open it. And this will create a solution where we only have one thing under our solution, and this is an exe. Now, debugging these is a little bit different. We can't just press start because there's no breakpoints by default. What we can do is right click, debug, step into new instance, and this will take us to our disassembly. Now in this case we actually also get the source because it knows where the source is, but this time the source won't be annotated because there's no debug database by the looks of it. Or potentially I can actually put a breakpoint, because we can set breakpoints and then we can hit continue until we hit them. And because we do have a debug database, I think it loaded. Yes, it did. Symbols were loaded here. So we do actually have access to this information. As long as the PDB, this file here, is in a path that Windows knows about, then it will find it. It also immediately checks right next to the exe, so there shouldn't really be any problems there. Okay, so now I'm talking about GDB, and this is our chosen command line debugging tool for Linux. There are other debuggers, I believe I mentioned Immunity earlier, that can be used for this. Those ones come with GUIs, they're useful, but GDB is definitely installed on pretty much all Linux machines because it's a fairly integral part of Linux. And it supports pretty much everything that you'd expect from looking at the Windows ones. The biggest difference is that it doesn't have a memory view because it's a command line tool. Instead it has the ability to dump memory. I'll show that later. It also has register tracking the same way that Windows does, although once again it's command line, so getting access to the registers is a little bit more tricky, although it will print them all in the event of like a segmentation fault or a sig kill, and it has a disassembly because a debugger wouldn't really be complete without one. So under the hood they're pretty similar tools, but there's no interface for GDB. So I'll switch over to a command line and show you GDB. So this is the section on GDB debugging in Linux. This is just an SSH box. This is incorrect. This is a command I typed earlier. Don't do that. GDB takes its arguments in a different place. If you want to pass arguments to the process that you're calling, it's not done on GDB's initial invocation. It's done later. There's two ways of starting GDB. You can either start it with this syntax, which will start GDB with the exe already loaded, or you can load the exe when you're within GDB. So if I just launch GDB, this time with the exe, so it's preloaded for us. And we can confirm that because it says reading symbols here. And we end up in this like kind of pseudo shell thing that GDB provides us. We can type commands directly to GDB here, like help. We can load files from here if we wanted to, but we already have one loaded here because we specified an argument, so we can just run, and the command is start. And there's a temporary breakpoint that is automatically put on the main function for you. You can also write break main to break that function if you want to. You can break on as many functions or addresses as you want, same as in Windows. I mentioned earlier there was a disassembly. The access to disassembly is by typing disassembly, but there is a short alias for it called disas, which will give us the disassembly of function main, which is where we broke. We broke on this line here, which is indicated by this little equals greater than sign, and we can see all of our program's compiled assembly. Now, the syntax here is a little bit different from the Visual Studio syntax. This is, I want to say AT&T syntax, but I don't think it is. It might be though. I'm gonna press enter to continue to read more. It's not the most useful thing in the world. We can actually look through individual functions if we want to. Right now, we disassemble by default. We disassemble the function that we are in. Help data. We can dump binary to raw binary files. This isn't quite what I'm after, because I mean, we just still need to disassemble it, right? So I'm going to use dump ihex memory, which will allow us to dump Intel hexadecimal memory to disk. Q enter. Reopen the disassembly window so I can find the name, and then just Q enter so that it keeps it on screen. And we're going to dump this memory malloc function. So I want to use dump ihex memory, and then we're going to type the name, which might take a little while because it's a fairly long name. And has some interesting characters in it. So part of this mangling has to do with the parameters it takes, which it is what it is. Missing start address. That should have evaluated the start address just fine, unless I mistyped it. Which I might have done. It's easy to do. Missing start address. Oh, actually, 1 second. It also actually needs an ending address. Oh, I got the syntax wrong. My bad. You actually specify the file first. Dump.hex, we'll do that. That now has dumped a hex file in the same directory that we launched this from, called dump.hex. My bad on the order of syntax there. And we dumped 16 bytes. So we can just add to these values here. Numbers, that arithmetic works. And because I'm in SSH, I can't just open up another terminal. So I'm gonna have to exit. Exiting GDB is done by typing quit, or by pressing Control D, which types quit for you, and presses enter. Now in this folder we have dump.hex, and we can use xxd, which is just another Linux tool, to have a look at it. And these are assembly instructions that I can't say I know what they are. There's a reason we have disassemblies. This is actually an Intel hex format, so it's not necessarily the most useful thing in the world, but that's how you can debug parts of code. For the most standard debugging, we'll just reopen this and we'll start. I'll reopen this assembly one more time to show where we are. We're at this sub here. We can step. Now, the step command goes forward a set number of instructions. So q return as a parameter. Now we can just write step to move forward 1 step. Or we don't, because I forgot how step works. Steps forward a line, but there is no line number because I know, I keep writing exit. The issue there, let me just scroll up until I recompile this, is that there is a flag for GDB that I totally forgot to pass. There we go. So now our temporary breakpoint isn't just set at a random memory address, it's now set at main arg c equals 1 and arg b equals this. We actually have line numbers now. Our disassembly should show that too. No, it doesn't. It just still shows a raw disassembly. There are better disassemblers. Well, not better disassemblers. There's better debuggers if you want a GUI. Yeah, one of the things we can do is we can examine the stack. This is... it's not that function, that's not its name. Yeah, so this can be really useful. We can also go up and down the stack. So we can do backtrace. This would be pretty similar to what you see in crash dumps when a program crashes. But right now we're only 1 level in the stack, so we only see main, because it's the only thing that we've called so far. We could step here, which will allow us to step forward 1 line. We now step forward to this line where we allocate our memory. we step forward, we so we're now in our function. Step is the step into function. We're currently stepping through the function that allocates memory and returns one of our templated pointers. It's line 22 of our source file. Now, if we were to write BT, which is the alias for backtrace, we will see two things in our stack frames. So stack frame 0 right now is memory malloc. This is our current frame that we are in. And then stack frame 1, which used to be our stack frame 0 here, is now frame 1. It's above us because the stack goes downwards. And it's just telling us where in the stack frame we are in the code that we jumped to this second frame from. Now if we step a little bit forward, I think step 3, let's not do that. Step 2 should do it. So now we've just tried to step into malloc.c. I guess I'm still in malloc.c. We're in an entry point in malloc.c. This isn't really helping anything. Let's step 20. We're still in malloc.c. Malloc is a pretty big file. And now we're out at this dereference, which is fine. So we're now, if we BT again, we are now within the operator here. We can step. It apparently steps to the end bracket. I don't actually know if that returns. No, it should be the return though. And now we step back out. So now our backtrace will show 1. This confuses me. I don't know how you can step onto a bracket, but apparently we can. Learn something new every day. So yeah, that's how you debug things in Linux. There are other tools in Linux like perf for performance profiling. That's another tool that Visual Studio integrates. So that should realistically be everything. Everything in the debugging section. The reason I opened this is because this is probably the most useful list of commands to bring up. Advance is up to a given location. So in Windows we had continue, and we have continue here too. It continues until it hits the next break. Advance will continue until it hits a given location. So effectively it creates a breakpoint at the location and then continues to it and then deletes the breakpoint. It's like a temporary breakpoint. Detach, we won't worry about those, they detach the process. This is mostly useful if you're using GDB to attach to already running processes. Like say you've got a process that's already running and you want to have a look at it, and you can do that if you don't want to launch it inside GDB. Finish, this is the command that I was thinking of earlier. This is where you step through until a current stack frame ends. So if you've gone to a function and you want to leave that function, it's like step out. In Windows, that's called finish here. Jump, which is something I've never actually had work on Windows, but works here. You can jump to a specific line of code directly from where you are. You basically just take a jump instruction to whatever specified line or address you put in. Kills are self-explanatory. Yeah, so the next instructions I've actually never used. They appear to be very similar to the step instructions. In fact, they appear to use the word step. So I don't know if they are just aliases. They might be. There's a few of those. Reverse. This amuses me. The program can reverse itself. I always find that kind of magical that you can step the program backwards one line of code if you want it to do that. Windows can do that too. I don't know how useful it is, but it can be useful. Run is where you start. Start is, yeah. This is one thing actually. I used star and it creates me a breakpoint. I also said you can break main and then run. If you just run, it will run the program without a breakpoint and it will finish without a breakpoint. Step is to a new source line. Step I is what I was trying to do at one point, where it steps an instruction. If you don't compile with right flags, then step does nothing. So step I is there. The targets are just for targeting exes. Until it just executes until the source line is greater than current. This is used for like escaping loops. If you get stuck in them, stepping through them can be pretty annoying.